Well, welcome. I guess we're thankful for COVID because now we know how to make these videos. And so sorry I'm not with you, but hopefully you, clearly if you're watching this, you've got the email and you knew how to find this. So let's just dive right in, guys. So last time when we left off, we had gotten to the idea of a left-hand limit and a right-hand limit. We had the new notation. We looked at this notation. The limit as x approaches a from the left of the function f of x is equal to L of the y value of the function, right? Equals L if and only if what? So let's see if we can write that down. I know you're chomping at the bit to get started. So here we go, all together now, right? Very nice. For every epsilon greater than 0, there exists a delta greater than 0, such that if, and then here's where the difference is with our just general limit as x goes to a definition, right? We only care about x being less than a, right? And so if this is a, yeah, we want to be over here some number of units delta to the left of a, right? That's where x gets to live. And so it's very easy to write down with that visual what is the inequality, the restriction on x, a minus delta less than x less than a. I heard you yelling it out. Very nice. Okay. And if that's true, then we've got the exact same conclusion we had before. We have the conclusion that the distance between the y value of the function at any x in here and the thing that is the limit, whoops, sorry, which we're calling L, can be made smaller than any positive number in the world. Now, I'm just gonna double check that this is actually recording and that you can see that from there, and it looks like we're good. Okay, so that's our definition for a left-hand limit, right? And then the right-hand limit follows super simply as well. We'll just write that guy down as well. For every epsilon, I know you guys are on it, for every epsilon greater than 0, there exists a delta greater than 0, such that if, okay, what's our restriction here, right? Now, we don't want x to be to the left of a, we want it to be to the right of a, right? As x approaches a from the right, so we can range, x can range a distance delta away from a to the right. And so again, the inequality of where x is allowed to roam in there writes itself. A is less than x is less than a plus delta. If that's true, then making this claim for this limit statement is the same as saying, again, the distance between the y value of the function at any x in here and the number we're calling the limit has to be able to be smaller than any positive number in the world. Okay, so those are our two definitions, and we looked at the definitions and we looked at the a graph and a visual representation of applying these ideas. And now we're going to look at a simple example, another example that's not graphical, but is instead involves this piecewise function that is also in your homework and in section 2.2, okay? So similar to a homework problem, this is 2.2 number 11. And what do we have going on here, right? This is a piecewise function. Why is it called a piecewise function? Because it's defined in pieces, right? For one piece of the function, when x is less than -1, the function is equal to 3 plus x. For another piece of the function, when x is in this range, the function is equal to x squared. And for another piece of the function, when x is bigger than or equal to 1, the function is this linear function, yeah? So now, you can have fun trying to draw that. That's not what I'm gonna do. That's not my purpose for this, but that's also part of the problem. But our goal here is to kind of understand these ideas. So for example, if I were going to say, right, what is the limit as x goes to -1 from the right, of f of x, what am I actually being asked now, okay? So remember, another important thing to think about, okay, that's limit as x is approaching a is our -1, and it's from the right, right? And so what's super important about this, right? Just like we know with a regular limit, when we see limit as x goes to a, that means x does not equal a. So same deal, x does not equal a. But we also know even more information, right? In fact, x is bigger than a, right? So when we see this, well, we know, right, that x is really bigger than a, yeah? And that's what helps us over here. If we're trying to determine this limit for this piecewise function, and x is approaching -1 from the right, yeah? If that's x, then x is bigger than -1, right? So that's telling me x is bigger than -1. I'm thinking about that, and I'm thinking about x, letting x get as close to -1 as possible through values of x that are bigger than -1. And when x is bigger than -1, right, but not super far away, yeah, what piece of the function is in play? Well, x bigger than -1, that's this piece of the function, right? Okay, yeah? X bigger than -1. And so what really am I being asked? I'm being asked for the limit as x goes to -1 from the right of x squared, okay? The limit as x goes to -1 from the right of x squared. Okay, so, well, we're going to get to some nice continuity results that are going to help us be able to evaluate these limits in very, very nice, simple ways. And if we have a nice little graph of this expression, right, x squared, if I look at the function x squared, right, this is a graph of x squared, then when x here is -1, right, and if I let my x's get close to -1 from the right, yeah, so here's such an x, and then I go there, and then here's such an x, and then I go there. And then here's such an x, and then I go there, right? My y values of my function are getting bigger and bigger, and they're actually similar to what the graphical things that we did the other day. They are getting closer and closer to this number right here, which just so happens to be the value of the function when the value of x squared, right? And this is a graph of y equals x squared. The value of y equals x squared when x is -1, and that is -1 squared, which is 1, right? Yeah, okay? So we're about to learn some limit laws that will allow us to evaluate these limits very nicely without having to do graphical work like this, okay? And so this helps us see this idea. So this guy is going to be 1, is going to be our limit, okay? So one of our goals is to move away from having to think about the definitions all the time, because we do want to know what things really mean, and they help us think about things. And we also want to move away from having to do graphical problems, which is what a lot of the types of problems that you have been able to do have asked you to look at and get information from a graph. So our goal is to establish, and that's going to be a little bit later, establish some rules that tell us, hey, well, you know what, if we did plug -1 in here for x, right, we would get -1 squared, which is 1. And so that actually does work, even though we know that that the idea of the limit has nothing to do with the value of the function. But sometimes they are the same. So when are they the same? That's kind of exactly what we're going to drive at, okay? So visually, you can attack this problem this way, and then you can also think about our ideas of what does it mean for a right-hand limit or a left-hand limit in a piecewise problem like this to decide which piece of the function are you in, and then you can draw that piece of the function and you have an idea of what the limit is. So, for example, if we did one more, whoops, that one has 2 if we did one more problem, what if we looked at the, going a little bit crazy here with these. What if we looked at the limit as x goes to -1 from the left of this function f of x, yeah? Well, if x is going to -1 from the left, right? Well, then we're no longer here. We're on this side, yeah? And what do we know? X is smaller than -1, right? Because we're in a left-hand limit. A is -1, right? And x is smaller than -1, yes? Okay? Well then, if x is smaller than -1, then what are we actually being asked? We're being asked for, that one doesn't write real well, so I'm not gonna keep writing with that. What is the function f of x when x is less than -1? Well, it's the function 3 plus x. When x is less than -1, f of x is 3 plus x. So I'm being asked for, what is the limit as x goes to -1 of, from the left, of 3 plus x? Yes? Okay? All right, well, now I'm just gonna erase this so I have more space. What does 3 plus x look like? What kind of function is that? Good, that's a line. Okay, so we're good at lines now. Linear functions, yeah. And so if we want to draw the line, what's the slope of this line? 3 plus x? Good, it's 1. What's the y-intercept? Good, b is 3, yeah. So here's that line, right? Okay. And I am interested in this line, right? I'm being asked really at this stage, what is the limit as x goes to -1? Here's -1, and I'm going there from the left, right? Okay. And so if x is a little bit to the left of -1, then I do that. Whoops, straight across. And then what do? I let x approach -1, and so here we are, and my number went up. And I let x get even closer to -1, and my number went up, and then x gets even closer to -1, and I went up, yep, right? And if we had a nice piece of graph paper here that was all, marked out, what number do you think that this, the closer we get, if we zoom out and keep getting closer, we're just gonna keep getting to there, but, but what is that number? Well, it actually really, again, kind of ends up being the y value of the function when x is -1, even though we know that has nothing to do with the definition of a limit, right? And so indeed, that is the case. If you had a nice piece of graph paper, just doing these graphically the way we've been doing them, that we would see that this limit is indeed 2, right? Okay? And so remember what was the limit for our piecewise function that was just here that I erased, right? Remember that the limit as x went to -1 from the right, right, of f of x for this f of x that we were talking about was the limit as x goes to -1 from the right of x squared, which we said was 1, right? And so the limit from the left at -1 is 2, the limit from the right at -1 is 1. Well, are we going to be able to get an epsilon bound? Are we going to be able to, for any epsilon that we pick, find a delta that will put us close to this on both sides? No. So the limit as x goes to -1, right, of this function f of x, you guys tell me, right, does not exist, right? Because we would violate the definition of limit that would say we have to be able to go on both sides and end up in that nice epsilon band around L, a single finite number L, right? Okay, we're going to expand and explore this a lot more soon, but for now, we've got our visual ways of thinking about that, okay? Awesome. Okay, so our next goal is to move on to talk about the ideas that are not on our quiz, and those ideas are related to infinite limits. Okay, so before I mention that, I just wanted to talk just a little bit more about a couple of the problems that are in 2.4. We've done several of those in your 2.4 WebAssign, and we talked about how numbers 8 and 9 in that WebAssign are related to the infinite limits as well, okay, so that's not on the quiz. And number 10 is a tricky one. That's a super tricky one associated with a non-linear limit. Again, to just let you see just how hard it is to really use the definition to prove non-linear, to come up with the relationship between delta and epsilon, the delta as a function of epsilon for non-linear limits, right, okay? When we did x squared over there, that's non-linear, but when we did 3 plus x and 2, that guy is linear, so the difference between linear and non-linear. So number 10 is for you to have some fun. There's an example in your book that helps you walk through that in section 2.4, so if you need a little more help on that one, take a look at that. The other non-linear problems that are in this section are number 6 and number 7, and those two non-linear ones in your homework, in your WebAssign, I'm referring to the 2.4 WebAssign problems now. Those two non-linear ones are special non-linear ones that work out nicely, and you can easily get a relationship between delta and epsilon. The other two, 4 and 5, are linear, and then we did 3 in class, and that guy's non-linear, but it reduces to something linear. So we're going to move to, in section 2.3, developing limit laws that will allow us to more easily evaluate limits with having developed the truth about what we can do and can't do, okay? So I think I'm gonna end this video here because the next piece, we're gonna move on and talk about how to adjust these types of limit definitions to figure out what we mean when we talk about, as the book says, infinite limits. We say unbounded growth, growth without bound, okay? So, be right back.